In this lesson, we're going to talk about the mean value theorem for derivatives. If the graph of a continuous function has a non-vertical tangent line at every point between A and B, then there is at least one point C on the graph between A and B at which the tangent line is parallel to the secant line through A and B. Now we have an if-then statement. So we have to have the if before we get the then. The biggest thing that has to be true about our function is it must be continuous everywhere on the closed interval from A up to B. We have to have that if, which we can see in this example, we have that. This is a continuous function everywhere on the closed interval from A up to B. Then we get this. If we have the if, then we are guaranteed that there is at least one point, here we're calling it C, on the graph, here's the graph, between A and B, at which the tangent line is parallel to the secant line through AB. So here's the secant line through the endpoints, A and B, and here's the tangent line. For lines to be parallel, it means that their slopes are the same. So this is the mean value theorem for derivatives says on a closed interval, on a continuous function, we're guaranteed that at least once the slope of the secant line through the endpoints will equal the slope of the tangent line at some interior point on our closed interval. That's all the mean value theorem for derivatives gives us. It turns out that this is kind of sort of a duh theorem, but it actually gave birth to a lot of relationships we could count on in calculus. Now here is an example. Here is a closed endpoint A, right endpoint B. It is a smooth continuous function on that closed interval. There's our if part. So we have at least one point on the interior of our interval A up to B. In this example, we can clearly see there are 3 points at which the slope of the tangent line is equivalent to the slope of the secant line through the endpoints. So we do see some mean value theorem for derivatives questions on the AP test. Here it is graphically. This is a graphical representation of the theorem. And we, again, have a closed interval, a left endpoint on our smooth continuous curve of A, a right endpoint on our smooth continuous curve here of B. So we have a closed interval from A up to B. We are guaranteed that at some interior point, the slope of the tangent line through the point of tangency will be equal to the slope of the secant line through the endpoints. And for us, the slope of the tangent line is the derivative. So this simply says, and I'm going to formally give you this theorem here in a minute, this says the slope through the endpoints, there's the rise through the endpoints, over the run. We are guaranteed on a closed interval, on a smooth and continuous function, will at some interior point, where C is on the open interval from A up to B, that the slope of the tangent line at that point C will equal the slope of the secant line through the endpoints of the interval. So let me formally give you that theorem. The mean value theorem for derivatives, if f is continuous on a closed interval and differentiable on the open interval, in other words, f prime exists, then there is at least one number, C, in the open interval, where the slope of the secant line equals the slope of the tangent line. Specifically, the slope of the secant line through the endpoints of the interval will equal the slope of the tangent line at some interior point or points, at least one. So there is the mean value theorem for derivatives. And we get all kinds of questions concerning that. We get them graphically, we get them like this, we get them analytically on the AP test. So this is something we definitely need to know. It's something that will give us free and easy points if we can just stick the mean value theorem for derivatives in our head. I want you to notice the equivalent form here of the mean value theorem for derivatives. Does anybody recognize y minus y1 equals the slope times x minus x1? It turns out that the mean value theorem for derivatives actually gave birth to the point slope form for the equation of a line. This is the point slope form for the equation of a line. And that is a product, a result of the mean value theorem, the mean value theorem for derivatives. So just a little interesting point. So verbally we say the slope of the secant line through the endpoints of the interval is equal to the derivative at some input value between those endpoints. Now that's only true if we're dealing with a continuous function on a closed interval. So let's do an example. Find the number c guaranteed by the mean value theorem for the function f of x equals 2 times the square root of x on the closed interval 1 up to 4. Well, the first thing that we're going to do is we're going to see if we have the if part of the statement. If f of x equals 2 times the square root of x is continuous on the closed interval from 1 up to 4. Okay, another perfect example of why we would need to know what our parent functions look like. So here is 1, here is 4, and sure enough, the root function, even though it's been stretched by a value of 2, is a smooth continuous function. So we're definitely going to be able to find at least one c value that lets us know the mean value theorem holds. So here's the process for the mean value theorem for derivatives. The first thing I want to do is I want to find my slope of my secant line through the endpoints on my interval. Okay, here's the slope of the secant line through the endpoints of the interval. F of 4 is 2 times the square roots of 4 minus f of 1, 2 times the square roots of 1, all over 4 minus 1. Well, the square roots of 4 is 2. 2 times 2 is 4. The square roots of 1 is 1. 2 times 1 is 2. 4 minus 1 is 3. So that slope is a positive 2/3. And now the mean value theorem says f prime at some c value is going to equal 2/3. So we need to find f prime of x. And f of x, let's write it so we can use the power rule. 2 times x to the 1/2. The 1/2 pops down front. 2 times 1/2 is 1. Reduce the power by 1. So there's f prime. So the mean value theorem says that there is some c value, we're calling it x now, where the slope of the tangent line, the derivative, equals the slope of the secant line. We could just as easily call this c. This is the c value it's talking about. So let's raise this to a -2. -2 times -1/2 just leaves us that value. This is 1 over 2/3 to the positive 2. So this is 1 over 4/9 or 9/4. Now we're guaranteed that that exists. We need to make sure that it does lie in our interval, because remember, c has to be between our endpoints. Well, this is roughly 2.25, and it definitely lies inside that interval. So there's our first problem analytically for the mean value theorem for derivatives. Here's a second example that I want to work through. Let f of x equal x to the 2/3 on the closed interval from -8 to 27. Show that the conclusion to the mean value theorem fails and figure out y. Mean value theorem. I need the slope of the secant line through the endpoints. So I need f of 27, and f is x to the 2/3, minus f of negative 8, all over 27 minus negative 8. So there's the slope of the secant line through the endpoints. I'm going to come down here and I want to talk to you about working problems like this without your calculator, because you're going to have to know how to do this. Remember that the numerator is the exponent and the denominator is the root. And possibly the best way to do this is to realize that 27 is 3 cubed, and we want to square that, and we want to take the cubed root of that. So we have 3 cubed to the 2/3. That's 3 cubed to the 2 times 1/3. When you raise a power to a power, you multiply. So the result of that is just going to be 3 squared, because we get rid of the cubed root. So the first part up here is 9. We could do the same thing with 8, because it can be written as negative 2 cubed. So the cubed and the 1/3 are going to cancel each other, and we're going to come out with negative 2 squared, which is a 4. And 27 plus 8, I believe, is 35. So this is 5/35. Oh, help me, I think that's 1/7. I think I'm right about that. So the slope of the secant line through the endpoints is 1/7. And now we need the derivative. F prime of x, power pops down front, reduce the power by 1, and we're guaranteed by the mean value theorem for a smooth continuous function on a closed interval that at least one interior value will equal the slope of the secant line and the slope of the tangent line. So I'm going to multiply both sides by 3/2. Hopefully we're okay there. I need to raise this by a negative 3, which means I'm going to have to raise that by a negative 3. So x is going to have to equal 1 over 3/14 cubed, or 14/3 cubed. So we'd have to figure out what that is. That's going to be a pretty big number. That's 14 cubed over 27. That's a pretty big number. Frankly, I think that's going to be bigger than 27. I'm almost guaranteed that's going to be bigger than 27. This is, sorry, I'm thinking here. My hand's not keeping up with my brain, or vice versa. This is outside of the interval. So the mean value theorem doesn't hold, and it says show the conclusion that it fails and figure out why. Well, I kind of sort of tricked you, because I didn't pay attention to the if part of the mean value theorem on purpose, because I wanted to show you that you can work a mean value theorem where it fails and actually get an answer. But it's not a useful answer, because what's true about our function on the closed interval from negative 8 to 27? If your function is continuous and your function is differentiable, well, it is differentiable, but on this interval, f prime is not going to exist when x equals 0. And 0 is definitely inside of our interval. So although f is continuous on the interval, it is not smooth and continuous. It is not differentiable at some interior point. And by that, the mean value theorem doesn't have to hold, because we don't have the if part of the if-then statement.